Let's compare the mechanisms of acid and base catalyzed hydrolysis because we need to come at ester hydrolysis from both directions later on, probably in the next video. Recall, all hydrolyses are just additions of water. So if we do a little bit of arithmetic, we add water across the carbonyl CO alkoxide bond. We break that bond, put the OH on the carbonyl, the hydrogen on the OR, and liberate the alcohol. Draw things in the same orientation as you added them, and then think about tidying them up later. Ester hydrolyses are biologically important. I'll give you one example. Acetylcholine is a neurotransmitter. It's found, for instance, at the muscle-nerve junction, and it has to be removed. And the enzyme that does that is acetylcholine esterase. Here is acetylcholine esterase. It mediates addition of water to give us this positive alcohol and an acid, and that modulates neurotransmission at that junction. Inhibition of acetylcholine esterase can be therapeutically useful, or it can be used for very evil means, like in nerve gases. Let's look at the acid catalyzed mechanism first. First step, protonate to activate, always in acid. That's what we do. Protonation of the carbonyl oxygen activates the carbonyl carbon towards the next step, which is nucleophilic attack of water. Water is attracted to the delta positive on the carbonyl carbon. The electron lone pairs push towards that positive charge. They push out electrons onto the oxygen, because you remember we can't have 5-valent carbon, and they neutralize that oxonium to an OH. That gives us this intermediate. It doesn't look nicely tetrahedral, so let's tidy it up, and now it looks like a tetrahedral intermediate. The next step is proton transfer, and you can draw this more simply, but I really like using a water to smoothly transfer the protons, because that's a little bit similar to what esterases do, enzymes that hydrolyze esters. Water approaches the tetrahedral intermediate, and think where we're going. Well, the tetrahedral intermediate is protonated on the oxygen that used to be the water. We don't want to make that one leave, because that just takes us back to the starting material. What we'd like to do is transfer a proton from that to the OR group, make that positive, and then we can push that out. That's where we're going. Water approaches with the hydrogen near the OR. So we'll use the lone pair on the alkoxide to push in towards that hydrogen. We'll break the hydrogen-oxygen bond and push those electrons towards the hydrogen of the OH on the tetrahedral intermediate, deprotonate that, and feed the electrons into the O+. So we have a push from the alkoxide lone pairs and a pull from the oxonium O+. So in the process, we've smoothly transferred a proton in the direction that we wanted. The last step is loss of alcohol. To do that, we push from the OH on the tetrahedral intermediate, that's now electron rich, in towards the carbon. We break a bond towards the oxonium, quench the charge, and methanol, in this case, leaves. If we've drawn everything in the same orientation, looks untidy. Let's tidy it up nicely, and we can see our acid and the methanol product. So in summary, the mechanism of acid catalyzed hydrolysis goes like this. Let's contrast that with base catalyzed hydrolyses. And in comparison, base catalyzed hydrolyses are so incredibly simple because we don't need any proton transfer. The first step is nucleophilic attack of the OH. Hydroxide adds to the carbon of the carbonyl, and it pushes the electrons onto the most electronegative atom, the oxygen. So we generate a tetrahedral anion this time. In the second step, the oxygen electron density of the O- pushes back in towards the carbon, and we allow the alkoxide to leave as O-methoxide. Finally, we have to correct this kind of unusual state here because we formed a carboxylic acid, which is much more acidic, much lower pKa than the methanol that would be formed by deprotonating it. The methoxide is much more basic. Can't have that. So proton transfer from the methoxide gives us a carboxylate. Consider this. It's a key point. Methanol is not such a terribly good nucleophile, and carboxylates, because they're negative, are not good electrophiles. So the reaction in base catalyzed hydrolysis is irreversible. Acid catalyzed hydrolyses, as we've seen, they're reversible, and we can adjust the position of equilibrium by adding more water or more alcohol. So acid catalyzed hydrolysis, a bit more complicated. Base catalyzed hydrolysis, like falling off a log. Easy, easy. I hope that helps with your studies. Thank you very much for listening. Bye-bye.